as well. So let's have a talk about the adjacency matrix. So what is an adjacency matrix? An adjacency matrix would look something like this, except it would be filled in with numbers. And it is like a matrix, which you would have covered in year 11, that records how many edges connect each vertex. And note also as well that this is a connected graph because everything here is connected. We don't have any isolated vertices. And another quick thing I'll draw your attention to is what is an example of a bridge. That's some more terminology you might need to know. A bridge could be this one here, for example, this one here, for example, or this one here. Oh, not that one there, actually. Sorry, that's my mistake. That's not a bridge. But this is an example of a bridge, and this is an example of a bridge. And I'll leave it to you to think about why. So coming back to the adjacency matrix, it records how many edges connect each vertex. So let's think about the number of connections between A and A. Well, there's nothing that connects A to A. A to A is the same vertex and it doesn't have a loop, so there are 0 connections connecting A to A. What about connecting A and B? Well, I see one edge, so we have one connection between A and B. How many connections between A and C? 1. How many connections between A and D? Actually, no direct connections, so we have 0, and we can actually fill in the rest of the graph. Some interesting things that I'll draw your attention to here is the connections between B and D. Connections between B and D is represented here and here. You can see that it's 2. And that indicates again that we have our multiple edges there. You can also see that C connected to C has 1 because this is a loop there. So there is one connection between C and C, whereas none of our other vertices have a loop. You can also see that adjacency matrices are actually symmetrical down their leading diagonal. So an interesting check to see if you've gotten it right there is to check if it is symmetrical down that leading diagonal. So in a directed graph, we can actually also have an adjacency matrix for a directed graph, but it will look a bit different and it likely won't be symmetrical down the leading diagonal because in a regular graph, the connections go both ways, but in a digraph, our connections are only one way. So they're not two-way streets, they're only one-way streets. So we only count the connection in the direction indicated. And we do this by assuming that we're counting the edge from the vertex stated by the row and to the vertex stated by the column. So to illustrate that, I've added our little labels here. So you can see here that A and C are connected, but we can see that it's a connection from A to C, not the other way around. So from is always indicated by the rows and to is indicated by the columns. So we can see that from A to C, we have 1 because there is that one edge connection from A to C. But if we have a look at, even though there is a connection there, if we look at from C to A, we can actually see that it's 0, and that's true because even though there is an edge there, it's a directed edge going in one direction, so it's only going from A to C. We can see, for example, that these multiple edges connecting B and D, one goes in each direction. So B to D is connected and D to B is also connected. So feel free to have a pause of the video and have a look at some other of the numbers if you'd like to explore a little bit more how they work. Alright, I'm going well for time. So, construct a network that represents the Facebook connections between friends and then construct an adjacency matrix to represent this. So first we're told that friends on Facebook work both ways. So if person A is friends with person B, then person B by default is friends with person A. So that tells us that we do not need a directed graph because the connections go both ways. Whereas if we were talking about Instagram, for example, we would be using a directed graph because we would say, well, they follow them, but do they follow them back? So we'd end up with that directed graph. But here we're talking about the both way connections. So the people we're talking about are Samantha, Jacob, Eliza, and Peter, and we're modeling their connections on Facebook. So Jacob is also friends with Eliza. We have Samantha is friends with Jacob, Eliza, and Peter. And a person can't befriend themselves on Facebook. So that tells us that we can't have any loops. And the network, like we said, I said it doesn't need to be directed because the connections go both ways, and it doesn't need to be weighted because there's no weight associated with it. A connection represents just the presence or absence of a friendship on Facebook. So how I'm going to draw this graph is I'm going to draw a vertex to represent each friend. One for Jacob, one for Eliza, one for Samantha, and one for Peter. And then I'm going to draw in edges to represent the connections between each friend. So I'm going to start with our first bit of information. So I can see that Samantha is friends with Jacob. So I've connected S to J. Samantha is also friends with Eliza and with Peter. So there, I've modeled our first bit of information there. And it doesn't matter if you set up or structured your graph or network in slightly different way, as long as it's displaying equivalent information with the correct vertices and the correct connections between the associated people, then that means that the graph or network is displaying the correct information, which is the most important thing. So next we can see that Jacob is also friends with Eliza. So I'm going to add a connection from J to E. And we know that a person is not allowed to befriend themselves on Facebook, so we have no loops. So we can see that there is our graph or network. And then we're also told to construct an adjacency matrix that represents this. And because it's not a directed graph, we don't need to worry about from and to, because all of these connections are two-way streets because we're talking about Facebook friends. And so that makes it a little bit simpler. And then we also know that it's going to be symmetrical down the leading diagonal. So S to S, 0 connections there because we have no loops. Samantha can't befriend herself. But we also know that Samantha is connected by one connection because that's the maximum we can have here because you can't be friends multiple times. Samantha is connected to Jacob, Eliza, and Peter. So we can fill that in. And then we can also fill in the rest of it. So we can see that Jacob is only connected to Eliza and Samantha. So we can see there's a 1 for Samantha and Eliza, but a 0 for the other people. Eliza is connected to Jacob and Samantha, and Peter is only connected to Samantha. And we can also see that again where it's symmetrical down the leading diagonal. So that's our adjacency matrix. So identify the vertex that contains a loop. Identify 2 vertices that have multiple edges. Identify the isolated vertex and identify a bridge. So the vertex that contains a loop, I'm sure you can see would be E because the edge is connecting from E straight back to itself. Can you see 2 vertices that have multiple edges? Potentially you identified A and D because you can see there's 2 edges connecting those 2 vertices. The isolated vertex would be G here, and the example of the bridge would be the edge connecting D and E. And I touched on bridges earlier because if we took away this edge, if we took away this connection, then our graph, it would actually separate the graph entirely. So it would no longer be all connected. G is actually already isolated by itself, so it already did have an isolated element of this graph. But if we did take away this bridge, we'd have those 2 separate areas again.